coming for the third day of the Midrasha. We're happy to have Assaf Reiner, who will tell us about explicit, lossless, and vertex expanders. Wow, it's hard to say.
Thank you, Michael. Thank all the organizers. I want to, before the talk, to dedicate a few words to Alex. Alex, I'm sure that you are familiar with the statement in the Talmud in Masechet Brachot that אין התורה נקנית אלא בחבורה. Meaning that the only way to acquire knowledge is by a group or within a group. And I think that this statement fits you very well. First, because obviously you are outstanding mathematician and group theorist. But more importantly, I think that it is quite remarkable to see specifically this week how many groups you gathered around you in the past 70 years, and hopefully also in the years to come. So thank you for teaching me this lesson, and Mazal Tov. So today I'll talk about explicit lossless vertex expanders. This is a joint work with Jun-Ting Hsieh, Alex, Sidhanth Mohanty, and Rachel Zhang. And I want to start with somewhat informal introduction about expansion in graphs, because we're going to consider several notions of expansion today, and it will be good in order to straight up the lines. And I'm sorry, I apologize in front of everyone who finds it a bit boring. We may take nap for several minutes, it's fine. So I think that the most general informal way to define expansion in graphs is the following informal statement. I say that every, let's say, reasonable subset of vertices has a large boundary. Okay, and by saying so, I didn't say nothing because I want to make this more precise, so I need to define what is reasonable and what is a boundary. And in fact, I can do that in several ways, and each way gives rise to different notion of expansion. So for instance, we have edge expanders. In which we take reasonable sets to be sets which are at most half of the size of the graph, and the boundary is just the set of outgoing edges. So geometrically we may think on these expanders as expanders without bottlenecks in some sense. We also have spectral expanders, which were discussed this week already. I'm not going to define them formally, but I'm sure that almost everyone in this room knows the definition. But roughly speaking, if we can bound all the non-trivial eigenvalue of the adjacency matrix, we have spectral expansion. And we also have this intuition here because an equivalent definition for these expanders is that every random walk on the graph converges very quickly to the uniform distribution. So I can start in a very small region of the graph and I propagate really fast to every other region in the graph. And the third notion, there are many more notions, but the third notion that we're going to discuss today, and this is the main notion we're going to discuss, is small set vertex expansion. Okay, and for this I will give a formal definition. By small set I mean set which is smaller than a constant fraction of the vertices in the graph, and expansion and in the boundary is just the neighbor set. So let's give for this a formal definition. So definition, G is a biregular graph. Okay, we say that G is a eta gamma vertex expander if I have the following, if for every subset, so G vertex set E, V and edge set E, every subset of vertices in G, which is less than eta fraction from the all set of vertices, I know that the neighbor set is more than gamma fraction than the maximal number of vertices I can attain. Like if the graph is irregular, I can attain maximum D times S neighbors, and in eta gamma vertex expanders, I attain gamma fraction of this maximum. And if I denote epsilon to be 1 minus gamma, which is convenient when gamma approaches 1, I say that G is a eta epsilon lossless expander. Okay, it's just a dual notion. And I want to think as an epsilon as a really small fraction, and thus I attain almost the maximum number of neighbors in the graph. Now, if most of the time today we're going to consider a biregular graph with left side, right side, and edge set. Okay, so if I have a bipartite graph, I can take two definitions. So I say it is one-sided lossless expander if let's say that the condition holds just for vertices in the left side. For every subset in the left side, and two-sided if obviously if also for every subset in the right side. Okay, so this is a really natural definition, and actually we can do everything today in the imbalance setting, in which I have constant degree in both sides but different sizes of L and R. But in order to me not to be confused, in order to use the notations today, I'm going to assume that the graphs are balanced, but I will focus on the bipartite case because this is the result, and this is the case that is interesting for many applications. And by saying so, I'll just mention few applications. There are many applications that are mentioned in Avi's paper. But let's just focus on coding theory. So we have many applications. The most basic one is the Sipser-Spielmann construction for LDPC code, low density parity check codes, which uses a slightly weaker notion actually than this notion, but it is implied by this notion. We can use lossless expanders in order to construct explicitly LDPC codes, and more recently, Lin and Hsieh in 22 used lossless expanders in order to construct good locally testable codes and also good QLDPC codes in a different construction from Panteliv and Kalchev, and also the construction of Alex, Shai, Irit, Ron Livne, and Shachar.
For LPC, they can use only one-sided.
Yes. So precisely, I'll get into that. Okay, so let's make a basic proposition. Okay, let's denote by ns equal 1 the set of unique neighbors. Okay, all the neighbors in the set S that has degree 1 back to S. Okay, so for instance, if this is my set, I have many neighbors here. So if I have something like that, this is not a unique neighbor because it has degree 2, and these are unique neighbors. Good. So it turns out that if I have lossless expansion, meaning this, I have also a unique neighbor expansion. But I need to pay some epsilon error. Okay, and in fact, many applications.
Try not to write there because some of the others.
Oh, sorry.
Yeah, it doesn't move. Yeah.
Okay. Okay.
Doesn't help.
So from now.
You can
move the.
Okay, and in fact, many application uses this notion. For instance, the Sipser-Spielmann construction. The notion of unique neighbor expansion is actually enough. Okay, good. And let's show some examples. So we can take, obviously, it is very common in expansion graph theory that we can take random graphs. So random graphs are with high probability lossless expander with, let's say, a D regular random graph. We need to take epsilon to be approximately 1 over D. Okay, so with high probability, a random graph is a good vertex expander, and it turns out that as for simple examples, that's it. Okay, we don't, for many years we didn't have more examples, and even if we take like everyone with intuition with spectral expanders know that the complete graph or the complete bipartite graph. So this is a non-example. The complete bipartite graph is a great spectral expander, but it is a horrible vertex expander, right? Because we don't have unique neighbors. If I have every subset which is bigger than 2, I don't have unique neighbors, so it cannot be a good vertex expander. So the intuition is slightly different. And for many years we didn't have more examples. Besides, we know that they exist, similarly to maybe spectral expanders, but...
What is the eta in the random case?
Sorry?
What is the eta rank in the random case?
Oh, I don't remember. It is... you can compute that.
Less than 1 over D, 1 over 10D.
Yes, okay. So, thank you. Also in our work, it's going to be... We can actually... track all the details, but we most of the time will refer to these graphs as epsilon lossless expanders with some eta, which exists, but I don't care specifically what it is. In our work, I don't going to track the parameters.
What's the upper bound?
An eta, I don't remember.
So the thing that is unclear is whether you have some fixed epsilon and some fixed eta for which
So
there is
I want to construct graphs. Okay, for any epsilon bigger than 0, I want to construct graph with eta, which depends only on epsilon and d. It cannot depend on the size of the graph. Okay, and when I tend to infinity, I want that this constant fraction of the graph will expand losslessly. Every constant fraction, which is less than a constant fraction of it. Okay, good. Let's mention some. So this is the forbidden area. Okay. So let's. Okay, so. Let's mention the history of this problem. So the first positive and negative result is due to Kahale. Okay, so Kahale showed the following. I just erased that, but Kahale asks the following natural question. Well, I have different notions of expansion. I have spectral expanders. And thanks to Alex and many more people, we know to construct optimal spectral expanders, which are Ramanujan graphs. So what would happen if I'll take an optimal spectral expansion? Would it imply good vertex expansion? And it turns out the answer is yes and no. So Kahale showed that Ramanujan graphs implies 1/2 minus little o of 1 vertex expansion, which is good, but it is not optimal.
It gives you no unique neighbors.
Yes, precisely. And Kahale showed that actually this is essentially tight. So, and this is tight. So Kahale showed that you can take a Ramanujan graph and destroy it a bit and to get a graph without unique neighbors at all, which attain this 1/2. And also a more recent work, this is Kahale plus Camber and Kaufman from 22, that Tali showed that we can take actual Ramanujan graphs and to attain this 1/2. Okay, this is Camber Kaufman from 22. So this is essentially tight. And in some sense, this is why this problem is so hard, because spectral methods fail here. Okay, it is not enough to take just spectral expansion, which we know to construct very well these years, and to hope that we will get a good vertex expansion. Although maybe it is the case in some cases, I think it is still open whether the LPS graphs are good vertex expanders. But the Ramanujan property by itself, it is not enough. Okay, good. And a breakthrough in 2002. So we have this day we have one-sided construction. So the first one was in a paper of Capalbo, Reingold, Vadhan, and Vigderson in 2002, who constructed one-sided lossless expanders using the zigzag product. For product, it was actually a variant of the zigzag product for conductors. But it is essentially the zigzag product. And more recently, two works of Cohen, Roth, and Tashma. So we have this, and we have also Cohen, Roth, and Tashma, which attend here from 23, and independently Golowich also constructed one-sided lossless expanders. Okay? And in fact, this is, as Pavel said before, this is enough for many applications. For instance, the Sipser-Spillman applications, it is enough for it. It requires only one-sided. And also, Lin and Hsieh constructed for LTC codes requires only one-sided plus group action. But we can use, for instance, the CRVW construction, and to make it to have a group action which fits it, and to get good LTC codes. But for the good QLDPC codes, we need, they actually conjectured at the time that they have two-sided lossless expanders with group action, and this was open at the time, and this is the problem that we're going to see the solution to.
The constructions of the CSP and the ROR are also coming from constructions of good expanders?
So I think that Amnon maybe is the right person to
It's
to
from
ask
high
this.
dimensional expanders, and the second one is from bivariate Ramanujan.
Yes, I think the Golowich also used the high-dimensional expander. He proposed.
No, Golowich only uses bipartite spectral expander.
But he uses also the one of these is the option in the paper is to use the phase vertex incidence graph as of the high-dimensional expander. I think I don't remember.
I think that's our paper.
Also in his paper.
Maybe.
Okay, which is interesting because we're also going to use some variant of high-dimensional expanders, cubical ones, in order to tackle this problem. Okay, good. Okay, so actually, our goal so it's obviously to construct two-sided lossless expanders. It was done actually in series of 3 papers. So the first one is due to Hsieh, McKenzie, Mohanty, and Paradis in 24. They managed to construct two-sided unique Naylor expander.
So the only problem is that it doesn't have a group action?
It is, sorry, it's not lossless. Expander, and also the gamma fraction in the definition was really tiny. So it was a breakthrough because it is a two-sided construction, but it wasn't enough. It was enough for Sidhanth, for instance, but it wasn't enough for many other applications. And the second paper is due to Hsieh, McKenzie, Mohanty, Lin, Hsieh, Lin, Mohanty, O'Donnell, and Zhang. They managed to construct two-sided 0.6 minus epsilon vertex expander. And this was a major breakthrough.
Gamma is 0.4.
Sorry?
The gamma I think was 0.6.
0.6 is the...
Epsilon was
Oh, epsilon is 0.4, but when I say vertex expander, I refer to gamma, not to epsilon. Okay. And this was a major breakthrough because it was the first time that someone broke Kahale's spectral barrier.
So can
Okay.
you specify what do you mean by 1/2 vector expansion? Can you write it down?
Sorry?
Which parameter do you refer to?
Okay, sorry, I should mention that. This is like gamma. When I say a gamma vertex expander or epsilon vertex expander, I just ignore the eta and I refer only to epsilon because this is the, I think, more interesting part. Okay, so this is just this gamma. And
What
we
is
have
it?
some
Did
constant
you write
data.
for the gamma? You never wrote it down. Just
I wrote it in
write
the first definition that I raised. Gamma is the fraction of d times s, okay, that I attain from all the neighbors. Yes, or no?
Is it known that like taking a power graph of a graph with some expansion doesn't make it a vector expansion?
Spectrally.
No, I mean, but in the
In this notion, I'm not sure, but it also, I want constant degree. So if I take power of graph, the degree is not constant. Okay? Thank you. And the third paper, which is Hsieh, Lubotzky, Mohanty, me and Rachel Zhang, we managed to construct a full two-sided lossless expanders for any epsilon. Okay, and let's take the theorem that we proved. So it says the following: for any epsilon bigger than 0, there exists some d naught integer such that for any d which is bigger than d naught, okay, I can construct.
Sorry, what's the gamma here in the lossless expander?
It's approaches 0. I can
The gamma approaches 1.
1 approaches 1. Epsilon can be for any epsilon bigger than 0. Okay, I can construct this. Okay, as there exists an infinite family of d-regular graphs denote them by Zi. Such that, okay, which are let's say eta, epsilon, lossless expanders. For some eta, which depends only on epsilon and d. Okay, but it's going to be implicit. We can track it, but it's going to be implicit in our world. And also, each Zi, we have a group action. We have a group gamma that acts on it freely with the following condition, that the number of vertices in the graph is of order of the group. And this is the condition that Lin and Hsieh need in order to construct good QLDPC code. So our work can specifically solve the conjecture that they raised, because we know that lossless expanders exist with high probability, but it wasn't clear at the moment that maybe can we construct them with such a group action, but our construction does that. And so this is the theorem that we proved.
But
Yes.
say irregular graphs, but they should be different.
Yes, I said in the beginning of the talk, I can do everything today in the imbalance setting, but I want to ease the notations on the board, because otherwise I will be confused. So yes, we can do that for any constant imbalance that we want.
Yeah, because for the
This
construction,
is what they need.
absolutely
Precisely, yes. Every Sips or Spillman type construction. I don't.
how big more or less is d0 compared to epsilon?
Oh, it's going to be huge. It's going to be exponential in 1 over epsilon squared. Okay, which is far cry from like the random construction. So this is an open problem, an interesting open problem to improve that. Good. It is huge. It is constant, but big constant.
Can you say a word about why you want the group action for applications, or is it
Yes,
for
it is for applications. So roughly speaking, what Lin and Hsieh does in their construction, they take two lossless expanders with a common group action, and they take the balanced product of them. And in the balanced product, we need to mod out the diagonal action. It is, and then we get like a square complex, which we associate with a chain complex, which is gives us a good QLDPC code. But if we don't mod out, it doesn't work. The action.
Here you're right. For any sigma I, what is sigma I?
Not for any sigma I, sorry, it's Zi. Every graph Zi.
All the graphs.
Okay, every one of the graph admits a group action. Fair? Okay? Good. Okay, So this was a bit long introduction. Sorry, wasting my time. Okay, but I think it is good in order to understand the problem. Now I want to describe the construction, and before I'm doing so, we're going to use in the construction the LPS cubical complexes, which are nice high-dimensional generalizations of the LPS Ramanujan graphs. So I'm going to describe really fast the LPS Ramanujan graphs because they were already described in Ori's lecture in Sunday, but we're going to use a specific property of them. So let P and Q.
Change the marker.
Where is the? Okay. So let P and Q be two primes which are congruent to 1 mod 4. And I'm assuming for simplicity that the Legendre symbol of P over Q is just 1. It is not necessary, but it is more convenient. It meaning that P is a quadratic residue modulo Q. And we define the following set, which is, so this is the LPS graph construction. Okay? From 88. We denote the set Sol P to be the following set. It is all the quaternions alpha equals A plus BI plus CJ plus DK, such that the norm of alpha, which is just the sum of 4 squares, equals P. And I want that A will be positive and odd. Okay? So I have this set of quaternions. I know that I don't need to describe them at this level as quaternions, but I'm going to use that, philosophically at least, in a moment. And by elementary number theory, it is Jacobi's 4-square theorem. I know that the size of this set is just P plus 1. Without this condition is 8 P plus 1, and this condition makes that precisely P plus 1, which is good. It is implied by this condition and this condition. Okay, good. And I associate for each element in Sol P, I associate the following matrix. Okay, it's going to be A plus B iota, C plus D iota, minus C plus D iota, and A minus B iota. Good. And iota is just the square root of -1 in FQ. And one can verify that the determinant of this matrix is P, and when I associate it in over FQ, it means that it is invertible. Okay, so this is in GL2FQ, but I decide to look at it as a matrix in the projective group in PGL2FQ, and specifically this condition implies that the determinant is squared, so it means that it is actually in the subgroup PSL2FQ. Okay, this is just basic group theory, graduate group theory game. Okay, so I have P plus 1 matrices in PSL2FQ. Good. And let's denote the resulting set as SPQ for alpha in Sol P. Good. And a proposition from the LPS paper is that first we have that SPQ generates PSL2FQ. This is not so easy to show because it uses strong approximation actually. And moreover, if we denote, so this is the proposition and theorem from LPS, Lubotzky, Phillips, and Sarnak, is that if we denote XPQ to be the Cayley graph of PSL2FQ with respect to this set, is a Ramanujan graph. Is a P plus 1 Ramanujan graph. Okay, so this is the construction. And we are going to use a specific property of this construction. So Ramanujan graphs, just recall that they are, in a symptotic sense, they are optimal spectral expanders. But this application, it doesn't appear in the Lubotzky, Phillips, and Sarnak paper, but it has an additional very nice property, which I'll denote as the meta-commutation property.
Used to me.
Sorry?
Used to me. New to me.
Ah, yes, but it appeared. Alex said to me that well, I know about it for 40 years, but I didn't do anything with that, and it turns out that it is quite useful. So we have the meta-commutation property, which is the following. So let's take two generating sets, two LPS generating sets, A equals SPQ and B equals SLQ with respect to two different primes PLN, but a common prime Q. We have the following amazing property that every pair of generators AB in A cross B has a unique pair in A prime time in A cross B, such that A times B equals B prime times A prime. And if we think of it geometrically, it means the following. We can start in a vertex G, and we can do a step in direction A to go to GA, and then in direction B to go to GAB. So GAB equals GB prime A prime, which means that we can do also this path. And this is a structure of a square complex. And this is look at the first glance as a miracle, right? Because I have two generating sets for a common group. If I have just two random generating sets for a group, I don't have a reason that they will satisfy this very special condition. But we can explain that in various ways. But I think the nice philosophy that lies behind it, and this is actually the most easy way to prove this, is that the LPS generators comes from this quaternionic world. And in the quaternions, we have a unique factorization theorem, but it is not a commutative ring. Okay? And when we formulate unique factorization theorems, we usually formulate them in nice rings, like we have unique factorization up to order. And the up to order never minds very much. But in a non-commutative rings, it is really interesting. And this is what makes this very special property to happen. Because I can factor every product of quaternions in multiple ways. There are many ways to look at it, but I'll just say, without explaining, that this property actually arises in many LPS-like constructions, actually also in the bigraphs of Hsieh and Ori. We can formulate some similar cubical property. So it is a miracle, but it is not a rare one. It seems to be not a rare miracle. So I think maybe everything in mathematics is like this. Okay?
You can give Hurwitz credit. Hurwitz was the first to Hurwitz.
Yes.
He's kind of important.
Yes, so this is actually also a question that number theorists in the book of Conway and Smith, they asked this question, and actually when we look on this from this perspective, it is not so hard to prove this result. Okay, good.
So if it's not there, do you know any example which does not count factorization in some algebra and Newtonian?
So I think it has to do with class number 1 and well, it is not surprising also if you recall that actually the universal cover of this object is just the product of the trees. So there we have squares also. If you take a suitable lattice, so you will have squares also there. Okay, so good. So let me construct now the LPS cubical complexes, which we are going to use. Okay, so I'm going to do the following. Let P1 up to Pk be different primes and Q all congruent to 1 mod 4, and I assume each Pi is quadratic residue mod Q. Good. denote by AI the ith generating set, and gamma to be PSL to FK. Good. And I'm going to define the LPS cubical complex initiated by P1 up to Pk and Q. Okay, as follows. So the vertices of this complex is just gamma, but I'm going to take colored copies of it. So if I have K generating set, I want to have 2 to the K colors. So for instance, in this picture, this is color 0, 0, this is color 0, 1, this is color 1, 0, and this is color 1, 1. Okay, it will be convenient for our analysis. Now, the edges, x1, is, I connect edges as follows. So Gx is connected toGai x plus Ei whenever I take a step in the ith generating set. So if I take a step in the ith generating set, I need to flip the ith color. Okay, and now I'm going to jump to the K faces. So what are the K faces? The K faces of this complex are all subsets of the form fx x running over all colors in x0. So I need to choose a vertex in each blob. Okay, but I need that they will satisfy some cubical property. I need it to be connected in order to close a square. So I need the following condition, and that if fx inverse fx plus ei will be in ai. Okay, so this condition actually ensures us that we get here a square or a cube. And I can define this way all the I faces using some sort of downwards closure with respect to this structure, because I need it is not like simplicial complexes that I can take just the general downwards closure. I need to respect this condition, but it is not so hard. Okay, and the key property that is used is the following. If I fix, so any K face is uniquely determined by picking a base vertex and a K tuple of generators. Where AI is in AI. And this is not so surprising, because look at the two-dimensional picture. If I'm telling you, well, I'm starting on a vertex G of color 0, 0, and I do a step A and B, so B prime and A prime are uniquely determined. So this is not so surprising, but it is really convenient for the construction and the analysis, actually. Okay, so after this long introduction, which I believe is interesting by itself, and if it is new to Peter, so I've done what I need.
I've heard it from Alex, but
I'm sure.
I'm glad to see it.
I'm sure. So let's turn into the construction. A basic definition from linear algebra 1 is the following. So let K be a power of 2. Okay, 2 to the R. The Kth Hadamard code, CK, the Kth Hadamard code. CK is defined as follows. It is the subspace of all linear functionals from F2 to the R to F2. Now I can identify this as a subspace of all functions from F2 to the R to F2, which is just F2 to the K. Okay, so I have here the Hadamard code, which lies in F2 to the K, and some basic properties of it is that its dimension is just R, it's just log 2 of K, because I need to tell you where each basis element goes, and it means that the size of the code is just K. Okay, and another nice property of it is that the Hamming distance of every x of every pair distinct pair in CK, the Hamming distance is precisely K over 2. Okay, so every two different code elements has the same distance between them. In fact, we don't need in the construction to use specifically the Hadamard codes. We need this kind of properties, but the Hadamard code is very concrete, and hence it is very convenient. Okay, so our graph is going to be product of graphs in some sense, and now I'm going to define the ingredients of the product. Okay, so definition. As I have my LPS cubical complex, and I assume that each of the primes are approximately equal to a prime p. I can do that, assume that the maximal prime of these pi's is at most, let's say, twice the minimal one, or something like that. And I'm going to define the base graph G left, with a left side, middle side, and edges, and also G right, with middle, right, and edges ER, to be as follows. So the left and the right side is just the K faces of the complex. Okay, the middle side, the shared middle side, it's the same M for both. It's just the gamma times CK. Now this is a subspace of, it's a subset of this set, so it's just subset of vertices. Okay, I take only the vertices that are colored with the Hadamard code. Okay, and I connect a face to a vertex if and only if it is contained in it. So it's, in some sense, the coded face vertex incidence graph. Okay? Good. So I have two graphs. And let's just note what are the degrees. So let's say that GL, gamma is always the group PSA. I work just with it. Okay, overlap. Okay? Good. And GL, what are the degrees? Okay, so I have a graph. One side of it is just the K faces. And I connect each K face to its Hadamard vertices. Okay? So if I have, so the left degree of this graph would be, okay, let's write like this. It would be KD regular, biregular. I momentarily say who is D, but the left degree is going to be K because I have the size of the code is just K. Okay, so the left degree would be K, and D is going to be just the product of all generating set, because we had the property that I already erased, that each cube is uniquely determined by a K tuple. And I have this many options to choose my K tuple, and in the analysis I refer to it as just P to the K, because all the primes are essentially the same, and each set is of size P plus 1, so this is roughly P to the K. Okay? So I have a KD biregular graph. And okay, so these are the base graphs, and the last ingredient I need to my product is the following. So,
Wait, so just GR is isomorphic but kind of flipped.
yes, in the imbalanced construction I'm going to take different generators in order to make this I will have DL and DR, and this helps me to like control the imbalance. But in our case, take it just to be there. This is why I wrote it like two graphs, because generally they are two graphs, they're not just the mirror picture. Okay? Good. Okay. Finally, let H to be a graph on vertex set D, EH, I will refer to it as a random gadget graph. Which I need to fix only once, because D is a constant. Okay? Pi I have chosen only once, so D is constant. So I'm going to pick H to be, think of it as a random gadget graph, which I may assume on it every property that holds in probability 1. For instance, it is great lossless expander, and it is whatever I want. Okay? I look for it in a brute force or something like that. And it has also another additional spreadness property, but I'm not want to get into that. Okay, so I have three graphs. I have GL, GR, which are just the dual of each other, and I have this random gadget graph. And let's get finally, after 45 minutes, to the construction. Okay, so definition.
Random doesn't obscure the...
Sorry?
The fact that it's random doesn't cause trouble with the group action property?
No, in the some sense that in zigzag you need group action just in a big graph, not in a small graph. It will not be transitive. But you have as this graph has group action, which they obviously have, it doesn't matter that this does not. Okay. But I need to connect H consistently in a consistent way. Otherwise, the action would fail. Okay, so good. So definition: the tripartite line product, which is also known to some of you as the de-randomized squaring. Is the topic of Gil's talk today, I think. Okay. The randomized squaring of Z of GL, GR, and H is the following graph. Is the graph on L, R, and edge set EZ, so I don't have M anymore, okay? I don't use it anymore. Obtained by, putting or placing a copy of H on top of every middle vertex M. Okay, so I know that this is not so formal, but this is best explained in a picture. Okay, so I'll just draw it. So I have a left, middle, and right. And assume I have the following picture, something like, I don't know, this. Okay? And I multiply it by a graph which has degree, which has the number of vertices on each side equals the left and right degree here. So it's 3 on 3 on this example. And assume it's something like, I don't know, this. Okay, of course, this is not a good expander, it is a cycle, but just for the drawing. So this is H, this is GL, this is GR. And the resulting graph is the same graph on L and R. Okay, so I need to draw 1, 2, 3, 4, 5, 6. Obtained by putting H on top of this vertex. Now, I didn't mention that. Okay, but we may assume that I have here some consistent labeling of edges. It is not so surprising because I know that each vertex extends uniquely to a cube, and I have a very natural way to do so. So I need to order in some natural way the k-tuples. It is not hard. I have such a numbering, and I put this gadget on top on this vertex, and it serves me as a switch. What does it mean? It means that if I'm here, I entered port number 1 in the gadget. Okay, so it means that I'm here. And here I can do a step towards here, and I exit in port number 1. So I connect this to this. And also I can do 1, I entered here, and I can connect in the to 3, and 3 exits in port number 3, so I do this step. And so on and so forth. Okay? So this is the construction. And the main theorem is as follows, so let me just write it. Okay, so the main theorem that we prove is as follows. So of course it is combinatoric, so by taking proper parameters, okay, which I'm not going to into that. So by taking proper parameters, Z, the resulting graph Z, which is the product of GL, GR, and H, is epsilon lossless expander. And of course, if I take Q, which is the size of the group, Q to the third, is the size of Q, approximately Q to the third, the size of the group, I get an infinite family of lossless expanders. Okay, so this is the main theorem. And in the...
So the main thing here is that epsilon does not depend on Q.
It does not depend on Q, yes. Yes, epsilon is, actually we choose it, yes. Okay. It is going to be like, K is going to be very big K's the dimension of the complex, but epsilon is not dependent on Q, and eta does not depend on Q. Okay? And in the, I have 6 minutes?
Yes.
Okay, so I want to just outline, maybe I'm not even going to write it, but outline what are the 2 steps in the proof, okay? And because this is the construction, it took me 5 minutes to describe it, but I think we saw a nice thing on the way. But the construction in some sense hints what needs to be the 2 steps in the proof. Okay, we need to analyze 2 things. We need to analyze from left to the middle, and this step, what we actually do is to show that if I take a small subset, most edges enter small degree gadgets. It means that the degree back to the pre-described set, the degree back is small. And this is good, because if most edges enter low degree gadgets, it means that I touch only few vertices in the gadget. And these gadgets are excellent lossless expanders. It means that I expand losslessly inside every gadget, almost every gadget. And this is good. Okay, so the first step is to show that almost all edges enter low degree gadgets. The second step would be to analyze the collisions. So the middle to right step is to show that different gadgets don't collide much. And this is some sort of a collision analysis. And I'm not going to get into that. There are many details in the proof. I can control the number of collisions when I go back to R. Okay? So I analyze actually what happens when I take 2 vertices of different gadgets. And actually, because I can translate this to question of edges and a great expander, which is not surprising because the cubical complex is like a great Ramanujan cubical spectral expander, I can bound the number of collisions. And the interesting thing that actually the mechanism that I described in this talk is, recall that I I mentioned 3 papers, and the technique in all 3 papers is the same. The thing that changed between them are the ingredients in the product. And in the second paper, the authors used the LSV simplicial complexes, and these complexes has the property that the links, they are simplicial complexes, the links of different vertices sees very different picture. And this property makes it very hard to control the collisions in the graph, okay? And this makes them to get a restrictive window of parameters, which gave them excellent result of 0.6 vertex expansion, but they couldn't push it further. Note that in the LPS cubical complexes, the cubical complex and the Hadamard code makes the link of every vertex to see roughly the same picture. Okay, because the harmonic distance is precisely 1/2. So every 2 vertices see roughly the same picture, and it makes the collision analysis much more uniform in some sense. Okay, it is implied in the analysis, but the philosophy here is that the cubical complex in this manner are more symmetric for this purpose in order to control the collisions, and because of it, when we analyze it, we get much more loose parameter window that you can use. Specifically, we can take k, the dimension to infinity, and this what helps us to attain epsilon lossless expansion for every epsilon. But I think it is nice to see in what sense the cubical complexes do here a better job than the simplicial complexes of LSV. I have 3 minutes. I just want to mention that I think it would be very interesting, as Alon said, to see more constructions, maybe with much lower degree, because the degree here is exponential in 1/epsilon squared. And also, I am specifically interested in looking for construction without this random gadget, because the philosophy here is great. Is like a local to global philosophy. I take a great local gadget and I amplify it using some high dimensional expander, but I get the feeling that I still don't understand how lossless expanders look in nature. Because I took a local lossless expander and we just amplified it. But I think there are much more work to be done in this area, and I think I'll stop here.
Questions?
So to get the quantum LDPC codes from that, to get the CSS codes, you basically use the GL and GR? I mean, it's the...
Yes, we take we take 2 lossless expanders. We need to choose them in very not symmetric way. It is really strange thing in the paper of Lin and Hsieh. They took two lossless expanders with group action like this, and they take the balanced product of them, but they construct them one after the other, and they choose the parameters of the second expander with respect to the first one. So the conditions are not symmetric at all, and it is actually it is important in the proof. It is necessary.
Important, so you cannot construct good codes.
Yes.
Otherwise,
Yes.
you cannot use the same code.
Yeah.
It's impossible.
Yes, you can't read of it. You can't read of it. They take like degrees that the second expander actually like swallows the degree of the first one, and it is so they take the balanced product of it, and the associated chain complex is actually which is nice because their mechanism is actually a chain complex which is associated only to vertices, not to like a vertex edge square or something like that. It's just the vertices of color 0, 0. To vertices of color 1, 0, 0, 1 to vertices of color 1, 1. So the chain complex is, in some sense, just on vertices, but of course there is a square complex. And the
exponential between epsilon and d somehow translate to the parameters there?
I'm not sure. Like it is enough for them in order to construct good LTC codes and QLDPC codes. but how does it affect the parameters? I'm not sure.
The parameters are all awful in all this.
Yes, yes. I hope that the LPS graphs are good lossless expanders, and then we will have great constructions.
What is the size of H?
So H is of size D, big D.
And what is B depends on?
D is theta of P to the K. And K is the dimension, P is constant, so it's exponential in K. And K is bigger than 1 over epsilon squared. Okay, so it is exponential, it is constant, but it is exponential in 1 over epsilon squared. So it is huge if you want epsilon to be very small. Okay?
Any other questions? Let's thank the speaker for a great talk.